Recording.
We're gonna get started. Second here. Okay. Screen. Okay, so as you know, today we're having the exam during the second half of class today. And then during the first half of class, we're just gonna do some slides. Okay, so this is kind of a summary of some of the topics that we've looked at. There is, the applied side of this, guys. All right, so there's the applied side of this, and then there's some of the theory behind this. I've given you some notes already, right? And today I'll just go over some concepts in a little bit more depth. All right, so that's the plan. I'm recording this session. Yeah, and then during the second half, you'll have the exam. Any questions before we begin? Okay, all right. All right, so let's go ahead and get started then. So it should be, I'll just use section 1 here. All right, so we go to the table of contents. So you have seen so far how to implement regression models, classification models, right, using PyTorch. Okay, so that's kind of the basics of the, you build neural networks really all the way to deep learning, right? So as I've said before, the next topic is going to be image classification. We're going to continue with a deep neural network, and then we're going to start getting into the advanced concepts of things like CNNs, et cetera. So make sure you understand those concepts basically. All right, so, and also, I haven't given you a homework because I wanted you to concentrate on studying for the exam, but look for the homework assignment, by Wednesday. There will be something there, and it'll be just implementing in PyTorch a neural network, reporting performance for some data set. I just haven't decided on what data set I'm going to use. I'm thinking something related to cybersecurity, and so I have some data sets there. I just need to look at it. Okay, and pick one. It's probably going to be like network intrusion detection. It's most likely. Or it might be a few data sets. It could be, 2 or 3 data sets. So I'm still thinking about it. But as I said, it'll probably be cybersecurity related. All right, so we've covered these topics, tensor operations. We're still gonna you should be, the 109 problems or so that I gave you, you should be practicing that constantly. If you get to the end of it, you know what? Start over. Muscle memory, right? So, in the time that I've gone over PyTorch, right, I've created these problems. So I think they are fundamental to many of the pieces that we're going to be looking at later on, like transformers, latent diffusion models, things like that. All right, so the 2 modules that I'm going to focus on for the first half of class today are these 2, loss functions and performance metrics. I don't want to drown you with a lot of theory. Definitely read the notes, but I'll go over some concepts in particular. I like the idea of contrasting things. So I have some slides on that, and that's in the loss function. So I'll go over that. And then also performance metrics is really important, right? So we're going to get into that. Usually what I do with my performance metrics lecture is I divide it into 2 parts, kind of introduce like a simple idea first, let you digest that for a week, and then we'll do the second half when we come back. Okay, so let's go ahead. As you can see, I have several slides here. Some are just on sklearn. And the reason why I have these is I use sklearn functions basically to calculate the metrics. We've already done this. I gave you a function, right? That's really important. So definitely read through these, but you already have this function in your code that I provided. So I'm going to just download performance metrics here. Okay. Here we go. So performance metrics. These are the concepts that I think are pretty important to understand. Yeah. In machine learning, we've talked about the pipeline. So you have that drawing, that kind of that picture of the flow, right? So you basically have a problem, you have X and Y, the data, a lot of data processing, the data science part, if you will, just so that everything is in the format that would go into a model, okay? Like a neural network model. And hopefully that's the common theme that you guys are seeing and how to create these. So this homework assignment will be your first challenge, right? To see if you can do it. So I'm not going to give you the code, but it's the code we've done in class, right? Does that make sense? So I'm just going to say, here's some data sets, do regression classification, and what will I be looking for? Performance metrics. Does that make sense? So I need to see a screenshot of the confusion matrix if it's a classification, or the RMSE or R square if it's a regression problem. Do you guys see that? So probably at least one regression problem. I don't know if in my cybersecurity data sets, I don't know if I have a regression problem, but so it might be from something else, but definitely for the classification ones, it'll be something in cyber. All right, so anyway, so your homework will have to have these performance metrics. So that's what I'm going to focus on today, right? So performance metrics and machine learning. So basically, as you guys know, what we do in machine learning is we divide the data into the train set and the classification and the test set, right? So that's what we've been doing. Sometimes you use validation, and that has its applications, although I don't generally do that. All right. There's also tenfold cross-validation. So that's when you basically take the data set and you split it into 10 bins. So you're going to do 10 iterations of the process, and you're going to take randomly 9 of those bins and use it for training and 1 of them for testing, right? So that way you're doing randomizing the data. So, you're going to get a performance metric for every bin, okay? So if you get a performance metric for every bin, then you can average them out across the 10 bins. And that's a more reliable metric than just doing it once. Now, this is what I've been mentioning quite a lot in my code when I say this is a poor man's cross-validation. You see, basically just I have a random seed when I split the data. And the fact is, even though in that one Jupyter, you're only doing it once, I'm sure you're going to be running your code multiple times for whatever reason, for trying to improve things. Eventually, you'll run 10 things, and it's equivalent to this. Do you see that? So it's not, and it requires a lot less code, right? So you just do that little seed, and then you just think that today you got an 86, and tomorrow you get an 81. You're keeping track of that in your head, and that's perfectly fine. Right? So, but that's the same idea. So we have these two approaches, but at the end of the day, what we want is some data for training, some data for testing. Remember, the test data should never be seen by the model. That's why we even use that with no grad, right? So that the model weights do not get updated. All right, so the metrics, I'll stress this because this is really important, right? So there's going to be classification metrics and regression metrics, right? So you've seen me do this in the code. Make a note of this. It's fundamental. And these are not by any means the only metrics in AI, right? So these are just like the very basic machine classification and regression metrics. In fact, there are many, many, many types of metrics. People are constantly creating new metrics. Nowadays, they're basically just using, for the advanced models, the large language models like ChatGPT or Llama, etc., they're actually at the level that they're giving them high school exams, right? So they're giving them high school exams and they're comparing to something similar to SAT scores and things like that. So it's gotten to that level. But we also have, for language translation, the classic example of transformers, it was the BLEU score, for instance, a type of a word error metric, but much more complex, right? So there's tons of metrics. And so that's really important. So if you ever want to compete in some competition, have your models be benchmarked, you're going to have to really study really well these metrics because you want to make, you have to make sure that when you say my model does like this, that you're sure of what you're seeing and reporting. Okay. So it's definitely the essence of everything. All right, so the metrics, I'll start today with the very basic ones and classification, which relate to the confusion matrix. So you've seen me print that out already, and I'll just show the relationship of accuracy, precision, recall, F measure to the confusion matrix. I usually skip the ROC curve. It's something sometimes people use, and it's another metric to have available. I did mention that a lot of these are, as you have seen in the code examples, they're just coming from the sklearn library. There's, what I do sometimes in my code is I'll use the sklearn library and I'll use the PyTorch library and I'll just put both values there. So we'll talk a little bit about R square also, which is what is used for regression, and some of the problems with it, as we go through these slides. So I'll give you some reading material on that as well. All right, so these are the function modules from sklearn that we've been using, and that's basically what I'm going to talk about today. All right, so we're going to talk about this idea. So the example I'm going to give you for you to understand the importance of this is something like this. So in healthcare, right, you have a medical condition, right? So there's a medical condition and you want that medical condition to be, detected, right? In some kind of a blood test or something like that. So what's going to happen is, some metrics are very precise in terms of finding all things that could be that. Even though eventually, if you make a more precise test, they're ruled out. You see what I'm saying? So this is a good example of the reason why we have all these metrics. Some metrics will favor, right, finding everything, and then other metrics will favor not finding everything, but the thing that it finds should be very precise, right? So I always think of it as casting a net, a wide net in the ocean, right? When you're fishing or something like that. So obviously, if you cast a really, really, really large net, right, you're going to grab a lot of, fish, things like that, but probably a lot of plastic, a lot, dirt, things like that, shells that you don't need, right? It's going to increase. Whereas if you have a smaller net, you have less of that debris, but also less fish. So then, but maybe it's more precise, right? So usually, like in medicine, you might have this example where they have a test that has, let's say, a high recall. So it captures all the cases just so that they don't miss someone that has cancer or something like that. It could have. And then once that happens, what they'll say is, okay, now can you please do a second screening? We're going to have a more precise test. And then hopefully that test will rule out. So it really scares the person, right, that got called in, but at least they don't miss that one person, that needs treatment. All right. So anyway, so hopefully that makes sense. I will do yeah, please go ahead. Well, we're going to talk about that. So it's all about the samples and what you look at, actually. So the metrics of, we're going to see how accuracy is calculated and how precision and recall are calculated. But what I can tell you is they're all calculated based on all the data in the test set, basically. Do you see what I'm saying? So that's why I'm starting here with the confusion matrix, right? So this is all the test sample. And so what we're going to look at is, okay, there's maybe two classes. So which ones were correctly classified and which ones were incorrectly classified. And from those bins in the table, we're going to select some for a specific metric like recall or precision, etc. You see what I'm saying? So it's going to be out of all of them. All right. But yeah, a good question. And then I will do a second example next week, which will be more of a cybersecurity type of a thing. We'll look at this problem again. But this can be tricky sometimes, okay? So, don't try to memorize it or anything like that. I usually don't advise that. to understand this, it's kind of nice to just look at this. This slide that I have here, you always start with the confusion matrix. So all the things that you see in classification, accuracy, precision, recall, they're all really just different ways of looking at the confusion matrix and getting some data. But that allows you to determine, okay, my model is really good at recall, is really good at precision, so on. And it depends also, like I said, on what you want. What do you want? Do you want, in the medical setting, you don't want to miss anything, even though you might get a lot of false positives. Does that make sense? Okay, so that's the key thing. And by the way, I'm sure you have taken a statistics class where this was called like type 1 error, type 2 error, or sometimes this was called false positives, false negatives, all of that language, right? So I'm not taking a statistical point of view here. We're just looking at this from a very practical way for machine learning, all right? But of all the explanations that I've seen, I've always really just liked to see it in simple terms like this. All right, so anyway, so this is the confusion matrix. So we're going to assume, and you guys can help me out. We can discuss it, but you can see here we have two classes, basically, class 1 and class 2. And so in the confusion matrix, we said that what we wanted was all the values to be in the diagonal, and any off-diagonal values, we would want them ideally to be 0, right? Because that means that if they're on the off-diagonal, then they are what? Errors of some type, okay? So that's the idea. So in simple terms, and this would apply also to multi-class things, but this is just a simpler example of 2-class. So basically, if it's a true one, then predicted is what the model predicted, right? So how many samples that were 1 were actually predicted as 1? And we're going to call that A, just so that we can use these letters to kind of work out how these equations basically work, okay? So we have A, and this is what we want. So of all the true, if there's 10 true, then we would want 10 to be detected, and this we would want to be 0. So basically, if it's true, if it's 1, but it predicts 0, then that's an error, and that's off the diagonal, basically, okay? And that's the same over here for 0. Then we would want D, we would want this to be 0, and this to be the number of samples that we have. Yeah, go ahead.
A quick question. I'm sifting through slides right now, and I was just wondering, accuracy, precision, recall, they're all measured from 0 to 1. Is that correct?
They should be, because if you look at this, we can look at the equations. A, B, C, D is going to be bigger than just A and D. We can look at this one, A plus C, and then A. So these are the counts of things that we're seeing. And then this one is A plus B, and it's A divided by A plus B. Make sense? So these are samples, basically. Yep. Right. Yep. Mm-hmm. All right. So, and then there's going to be F measure, which is a specific metric that combines precision. So let's go back here. So the accuracy is going to be basically, given this table, the confusion matrix, the accuracy is going to be A plus D divided by A plus B plus C plus D. So if you look, these are all the samples that you have in your test set, right? So of all the true, 13 correctly classified, and let's say 2 incorrectly classified, for a total of 15. But that accounts for all of them. Do you see that? And the same goes for true 0. Of all the 0 cases that we had, let's say there's 20 of them, 19 were correctly classified and 1 was misclassified. So it should give you about 20 samples. Make sense, guys? All right, so then basically here, the equation was A plus B plus C plus D, all of them, that's the denominator. And in the numerator is A and D. A and D. So the values in the diagonal. And that's going to be your accuracy bet, basically. All right, what you will see sometimes when you have a balanced data set, and that's like Iris, for instance, where we had 100, 100, 100, or 50, 50, 50, sorry. Accuracy is actually a good metric, right? But unfortunately, when we have it, like we do in most real use cases, an imbalanced data set, accuracy may not be as good. Okay, so that's not so obvious in this example, but you will see that I can tell you from experience that accuracy is not a good metric when you have highly imbalanced data sets. And instead, I would recommend using the F measure and also doing a per class, looking at each class and how it performs, basically. All right. Precision, let's take a look at this one and let's think about it intuitively. So precision means A and C in the denominator. So what does that mean? Out of the predicted, how many were true? Do you guys see that? So it's A in the numerator and A plus C in the denominator. So just imagine that I'm drawing here like a circle, right? So we just look at these samples. Of the samples that we predicted, how many were actually correct? And that makes sense as in terms of precision, right? Because we just want to know, okay, it said these 6 cases. Are all 6 cases what we were looking for? Yes. Okay, that's great. That's what we wanted. It's good precision. Do you see what I'm saying? What's the problem with that, though? The problem with that is, you may miss some cases by having, if you build a model that has high precision, unfortunately, it may miss some cases. Okay? So that's the idea. Because here we're only looking at predicted values and not all values. You see that? So remember how machine learning works. Machine learning works basically on a loss function of some kind, some objective, and that objective changes the weights, the model starts predicting, and then you have all these metrics: accuracy, precision, recall. So which one are you training the model for, right? Which performance do you want to be the highest? So if you start focusing on just precision, you're going to have a model that's pretty good at what it finds, but it may be missing some things. Because it's like it doesn't look at everything, it only looks at this part. Got it? All right. Now let's take a look at the other flip side. In the example here, A and B. So basically here the recall is A and B. So out of all the real values, right? So it's A divided, so A in the denominator and A plus B in the denominator. So it's saying out of all the values that are 1, right? And if I kind of highlight these 2, how many were correct? Okay, and that's called a recall, basically. That's a metric, is it finding everything in the population? Do you guys see that? You're trying to optimize. That's kind of, again, you look at that example of, well, if it's all the samples in the population or in a group, right, of some illness, right? How good is it at detecting all of it? And you want to optimize the model for that to be good. So you're just going to be concentrating at this. So in summary, you can build a model that looks at everything. If you look right at everything, or it just looks at A plus C, or it just looks at A plus B. Got it? And you can build your model towards those individual goals. Nowadays we can even train models, especially like large language models, that have there's tricks that we can do, right, to make the text that comes out of those models be more emotional, right? Or it can be more like horror, or it can be, it's the same idea in a sense, right? Because the point is you're always optimizing some metric that you have identified. Okay. But this is the simplest example that we have looked at. And then the final score, which is actually the one that is recommended for machine learning for classification problems, is the F measure. And the reason for that, as you can see in this equation, is that it actually, after you've calculated precision and recall from you would use these 2 equations, you combine them in one single metric, right? And then that metric actually is it finds an optimal between precision and recall. It's not just an average of the 2 values. We will see this a little bit later next week when we do the second half of this lecture, that the intuition is that it kind of penalizes if it's going too much to precision or too much to recall. It kind of wants a good equal weighing of both of them. So whenever you're dealing with a problem, you kind of want a model that has an okay precision and an okay recall. You don't want a model that has great precision but terrible recall, or or the other way around. So in that case, the metric that you would look at, which you will see this a lot in classification papers, is the F measure. Make sense? All right, so these are them, and then of course everything is coming from the confusion matrix. Now, of course, I've given you these equations only for you to have some intuition about them. Usually, we'll just calculate them with sklearn or something like that, and so on. Okay. Let's say you're generating images, right? So nowadays we have generative models, right? In a generative model, you give it some text and it generates an image. An image that you don't have another image to compare to, right? So there's no like measuring classification or performance. So then you need specific metrics for that. And some of these metrics have to do with the measurement of noise. There's a lot of metrics that you can have nowadays in large AI models. All right, but in essence, these are the basic ones for classification. The confusion matrix, we have looked at this one. I think this is pretty familiar to you. Okay, so remember what you want is values on the diagonal. Whenever possible, print out this for a multi-class problem. Okay, and it's ideal to get those metrics, F measure, precision, recall, accuracy, on a per class basis, especially if you have largely imbalanced data sets. Okay. So again, your homework assignment will require you to report these metrics if it's a classification problem. Okay. All right. All right. This is round 2. So this one, I kind of don't do this one today. I'll do this in the next lecture. I want you to kind of process this information, read through the case, but it's a nice case of, security, I guess, and a highly imbalanced data set, right? So finding terrorists in flying, right? In airports. So obviously most of the people that fly are not terrorists, right? So only 19 confirmed terrorists between like 17 years, right? So it's a highly difficult problem. So read through it, and then we will come back to it next week. And then basically I'll do the same thing, but I'll just put it a little bit more in the language of true positives and false positives and so on. This is a topic that can be a little bit confusing, so I like to keep it light whenever we address it, okay? But definitely read these slides as they are pretty important. So I will come back to this one. And then just to kind of point out, I've already given you this function, so this should look familiar to you. This is in the GitHub, and you have used it before, so you will use it for your homework assignment. So this is just all the details of that. Any questions? Now, if you do a regression problem, remember, I believe I gave you the R squared. We did that, right? Yeah, we did that as one of the metrics, so you'll have to report your results based on that. MSC is another metric that you can use to report your homework results, okay? All right, so anyway, so we've covered part of that, and which will be useful for the homework. Yeah, I've done this. All right, and then I'll just kind of briefly go over these other slides just to make sure I've like shown them to you. That's what it is. Is that a Jupyter now? Okay, this is, yeah, this one. Sorry, I meant to click on this. So this one I'll just briefly discuss as we have looked at this code. Yeah, so this should be short. Okay, so sklearn, some information about it. sklearn is some library in Python. It's been around for a long time. Don't use sklearn for your homework. That's basically except for performance metrics. If you solve any of these cybersecurity homework data sets with sklearn, I'm going to give you a 0. Okay, you have to use PyTorch. Okay, this is a common thing that happens with students. So I want to stress that, right? So we're only using, the whole point of this class is for you to like learn how to build complex neural networks, right? You're already building deep neural networks in PyTorch, and you will keep doing that. If you want to learn sklearn on your own, you can. I promise you. Once you finish this class, sklearn is going to be like hilarious. Okay, so you can do that on your own. But I'm not saying it's bad. That's, I'm not at all saying sklearn is bad. I'm just saying the whole point of this class is PyTorch and neural networks in particular. sklearn will have neural networks, but it'll have a ton of other classification algorithms that I don't cover in this class. If you want to learn about other class of KNN and all that, take 365. All right. So anyway, so sklearn is only to be used for performance metrics, confusion matrix, things of that nature. There's the libraries. We also use the train test split. That's okay. You can use that. I use that heavily pretty much all semester. That's a lot of people actually follow these same patterns. So it's not just my preference. There's the function again that I provided to you, and that's kind of my little spiel there, right? So only PyTorch, also no TensorFlow. I don't like TensorFlow, but I'm a fan of PyTorch, and a lot of, I can tell you, a lot of the cutting edge stuff. If you want to really implement it, PyTorch is going to be, a really good resource. Also, okay, so, all right, so that's those slides. All right, so we finished that module except for the example of terrorism. We'll, as I said, read through all those slides so you understand very clearly, and then we will come back to that topic next time we meet, okay? All right, so now the next module I like to discuss, kind of you can see here, is loss functions. And I have several ideas here. It's a lot of neural network things. And it's basically a contrast of different architectures, different loss functions. And I think that's might be a good way to learn about these things. So you see I have some PDFs, right? So I have this one. Okay, so I have all right, so let's take a look. So this is about neural networks, right? So neural networks historically might have started with something called a perceptron in the 1940s. I'm not going to cover the perceptrons. There just wouldn't be enough time. Okay. Plus, it's not, like state of the art, right? So you'd be wasting your time implementing a perceptron in PyTorch. I mean, do the proof or whatever, the math, but you're not going to build a chat GPT with just that one perceptron, right? So scale up, although it's a pretty good background and some of the ideas are there. But you can see here I have just basically I have the perceptron and I have linear regression, logistic regression, and neural networks. Do you see that? So this terminology, perceptron, linear regression, logistic regression, and then a neural network. So they're all neural networks. They can all be coded in PyTorch, right? So and we've done regressions already, and we've done classifications, basically. So I have this kind of these slides here. So everything is related to this function that you've seen me talk about. Y equal mx plus b is the equation for a line, right? So, and this is, I would say one of the most fundamental equations in neural networks. It gets way more complicated than this, but actually it starts here, right? Remember that we rewrite that function to be y equal w x plus b to be more consistent. So the m that, in a line, the slope of a line basically here would become the weights of the model. All right. So remember that what we do is we have inputs x, right? And those x's, think of it in a simplistic way as being multiplied times some w plus this beta. And then that's just going to predict the y. And that is the thing that we're all like, it's going to destroy the world. It's going to take our jobs, all that stuff. Well, because they're just much more complex than this one little equation. In fact, they're just like stacking these equations, making them deeper and so on, right? And we will see this as we start looking at CNN, so as we start looking at a GPT, it's just a lot more, in fact, okay? So, you can think of the perceptron. You got two neurons, and, two inputs and one output. Remember, the lines just represent the W here. The X are these two inputs. B would be something that you can add here at the end once you've predicted a value here, okay? But it is, in essence, a neural network. The other equation that I think is pretty important is this one. This is J, by the way, is the equation that is used to denote the loss function. So in machine learning, there's basically these two equations, the inference equation or the prediction equation, and then the objective function. So if you look over here, the J equal MSE is basically this equation here. And to fully simplify it, you can say y hat minus y squared. And what does that mean, basically? Y hat minus y squared. So you can think of if you imagine that this is y hat, then this is an equation that you learn, right? And that equation predicts values. And then those values you compare to the actual value. So y hat is the predicted value and y is the real value. So then what do? You take the difference between the two, square them, and let's say, forget about training and everything and all the complications. Let's imagine that we randomly pick the values, right? So we have this equation, we randomly pick a set of weights and b's, and we give it the x, it predicts a y, and then now we have that y, the predicted and the real, we take a difference, and the difference is 20, right? Do you see that? Next time around, what do? You pick randomly another set of weights and b, so w and b into x, it predicts a value for y hat, which is 3. And the real value was 5. So now the difference is less. Do you see that, guys? So then basically what does that tell you? The second set of weights is better than the first set of weights. That's it. Like if you had a quantum computer, think about it, and the quantum computer could right now predict all the possible combinations of weights, you're done, right? You do that in parallel, and the one that has the best result lights up. That's it. You wouldn't even need to train. We don't have a quantum computer, so we can't really do that, right? So obviously then what do we need to do? We need to find smart ways of finding these W's and B's, and that's where we start to get into this whole process of how to train. But let's keep that for now. So again, then, as we are doing machine learning, we're going to have a prediction equation, and then we're also going to have an objective function, two functions, okay? So here we can see the linear regression model. Basically, think about it, is just we have some points, right? And we are predicting a line. Remember that intuitively, we know that this was a line. We learned this in high school. So you can see that you can fit this line to some data. All right, and so the architecture of this network is basically, let's say, 4 neurons to predict one neuron where the values are from -infinity to infinity. So any number. You don't have to do anything beyond that. Do you see that? That's regression in its simplest form. And it's only in its way where I'm just contrasting one thing to the other. So logistic regression, right, is more of a classification problem. All right, so in this case, if you notice that all the dots here are red, right? Whereas here, my dots, some are red and some are blue. Do you see that? So there's going to be a different goal or a different objective. So in this case, the objective is to create a line that fits the dots. In this case, is also to create a line, but the line is going to be turned in a different direction. And what's the objective? That the blue dots would be on one side, the red dots would be on the other side. All right. So intuitively, we can understand it like this, and then we just have to start to think about the objectives that will give us that, basically. All right. So remember that we've done this already. When we did the regression example, we did MSC, and when we did the classification example, we did something called cross entropy. All right. So that's the basic idea. So here, the logistic regression example, notice it's very similar. You have four neurons, but now you can run this through some kind of a function. Okay, and this function now shrinks the data into a range such as 0 and 1, basically. Okay. So anyway, that's one of the intuitions. And then from there, we can extend this to higher architectures with neural networks. So we'll cover this a little bit later. So I just kind of want to go over this intuition, some of the intuitions here. So let's take a look at regression again, which is the most intuitive case, as logistic regression can be a little bit less intuitive. So in linear regression, and in basically in a machine learning problem, we have, as I said, two equations. Think of it that way. In its simplest form, we have the inference function, and then we have some objective function known as the loss function. Okay? So the other way that you can think about this problem is that you have two charts or two graphs. Okay? So this chart, totally separate. I mean, they're related. These two are related, but they're not the same graph. Okay. One represents the behavior of this equation, and one represents the behavior of this equation. Okay. So for your actual data, right, you're going to learn the parameters that give you a line that goes through these dots perfectly. Does that make sense? And so whenever you're looking at a machine learning problem, you will look at this data. But on the other end, you have this other equation for the regression problem. Okay, and in this case, you'll have, if you notice, now I have the right notation. I have the model that I'm training, which predicts y hat, and then y hat is going to be compared to y real. So we train a model to predict values. Those predicted values are then compared to the real values, right? And in this case, intuitively, we just try to minimize this error. So every time we're doing something, we take a whole bunch of predictions, compare them to the real values, square it to get rid of like negative effects, and we look at that value, and it's 75. And then the next time we do things to the weights, again, predict a whole bunch of values, compare it to the real, and now it is maybe 13. So what does that mean? That difference has gone down, and our objective was to minimize that error. So intuitively, this is something called a quadratic function, and it has its own chart, right? Which represents the behavior, if you look, of this equation here, right? So of this equation here. So as we start to move, you can see here in the x-axis, we have the parameter w's, which are related to this y hat, because y hat is written in terms of wx plus b. Do you guys see that? So think of it as where you have w hat here, you would now plug in this equation. All right? And so now that brings these parameters that you learned into this equation here. And then from there, as you start modifying that w, things are going to start moving in this equation, and basically their representation will be like this. Okay. So again, we'll come back to this topic later, but for now, I just want to give you a little bit of the information of it. Okay. So in summary, in machine learning, you're going to have these two equations. Look for them. This one is what? The neural network, basically, right? So get some inputs, get some outputs. It's going to get pretty big. And then this one over here is going to be the loss function, which is usually just entropy, binary cross entropy, multi-class cross entropy, or MSE. okay? But keep in mind, they will have two different behaviors. This is only for MSE, by the way. I'm not saying this is the actual, this is just a classic thing you see in the simplest regression model for intuitive purposes. We'll get into this a little later in the semester. Okay, so I'm not even going to touch cross entropy right now, so we'll talk about that later. But I just want to touch on some of the ideas that we've talked about before. So another thing that we've talked about before was the sigmoid function. So you can see that here. Basically, it's written out. We did this a couple of times, right? And the idea was that we had values from a scale of -infinity to infinity, and they just get mapped to 0 to 1, right? So we talked about that already. Here is the equation for it, and here's a little graph of how that works. So basically, any value between -3 and +3 now would be in a range between 0 and 1. Okay? All right, so for now, I think, I just want to touch on some of these things. Let's look at the other one where I also have a contrast. All right, so you can see here I have a little bit more information, but it's kind of the same idea, right? So neural networks, perceptron, we're kind of not looking at that one in this class, but we are starting at regression. We definitely did a regression, then logistic regression, multi-layer perceptron, deep learning. Okay, you guys have in fact coded all the way up to here, right? We've done a deep learning model. So again, what is some of the terminology? So you can see it's basically the exact same thing every time with just subtle differences. Okay. So the perceptron was, you can see it's the same equation initially, and it had a simpler update or optimization process, right? We'll skip that one. Linear regression, this actually we coded in class, right? So you built a neural network. What did you use to represent this equation here? We didn't actually code Wx plus b. What did you do? Or what did we do? We wrote the code for this, right? You guys remember, we did a regression and we did this equation Wx plus b, but we didn't hard code it is what I mean. Although I did say this is that. Do you remember what construct that was in PyTorch? NN dot linear, exactly. So NN dot, so it used to be that you literally had to write these out, right? Hopefully you're going through the 109 problems because it's also there, okay? But yes, NN dot linear, this is, if you just do PyTorch and are always using NN nonlinear, but don't make this connection, you're missing something, okay? You should have that intuition that NN dot linear is actually just a Wx plus b. When TensorFlow 1 came out, there was no NN dot linear, but that was in 2015 or 16, right? And what did you have to do back then? You had to create a variable, right, for W, and a variable for B, and a variable for X. You had to literally create them and then build the equation and do all that fun stuff. Now, PyTorch just allows you to do .nn.linear, and everything is like instantiated for you initially, okay? But you can get we've gotten the parameters and everything from there. So anyway, this is really important, right? So nn.linear does the heavy lifting, and you have seen how we have been using that in the network. Initially, it'll just predict from infinity to infinity, depending on the data. How does this function train? As I said, you're going to give it some X values. Imagine randomly it just picks W and B, predict something. Boom. You predict that value, and you're going to compare it to your real data. And then you need to intelligently decide what you're going to do. Do you see what I'm saying? We'll look at the gist of how optimization works later. But for now, just these W and B's need to be changed based on something. So they're going to be based on the idea that you have the real data, you predict, you compare those two, and then you use that difference to as some piece of information to make a decision. Okay. And that's going to be something called the stochastic gradient descent. So, but the loss function for regression is going to be something called MSE, mean squared error, which is actually an intuitive way of thinking about things. All right, logistic regression is what we're going to be using for classification problems. So we'll see that later. Notice here, really the difference is, whereas here we had a WX plus B, now we can call this one Z, and it goes through some function, right? And this function then is we're going to use that information to start doing classification, and the loss function is going to be cross entropy. All right, so we've done this in the example so far. So, we've done this already. So that's the terminology. All right, so this is just logistic regression. Now, multi-layer perceptron, if you notice, what is happening now is you have the same WX plus B, but it produces C. It goes through a function that now calls it H, right? And here comes the insightful part, hopefully. Notice what happens to H1. Now you have W2 times H1 plus B2 to produce C2. So it's just another one of these equations, right? Another one of these equations. But initially, you started with X here, and over here, it is now H1. And what is H1? It's just a result of the previous thing. So it's basically just functions, right? And these are the layers of a neural network. So when you talk about a deep neural network, just think of your data going through all these functions. Okay, and then you have something called cross entropy. So you start at this point when you start building things like this, you start to need specific algorithms, stochastic gradient descent to do these things. Those are separate algorithms. You don't actually have to code these in PyTorch. That is the reason why we need PyTorch or TensorFlow, because that part of the process is just like almost abstracted completely for you. That's the beauty of it, right? So they almost completely, but it's a lot goes into this. All right, so now let's look at a deep learning algorithm. So what is deep learning? Basically, it's like the multi-layer perceptron, but if you notice here, X times W plus B produces C1. C1 goes through F, which produces H1. That's like the first layer. Then H1 is multiplied times W2 plus B2 to produce Z2. That goes into F and produces H2. And that's like a second layer. But you can just keep doing that, dot, dot, dot. And then let's imagine that we are at, what is that? Hn minus 1 times Wn plus Bn, and that produces Cn, which goes through a function which produces your final Y. Do you see that? So it's always like just going, the result of the previous one becomes the input to the next function, and the result of the previous one, and so on. And that makes it deep. And we literally code it this way, okay? So hopefully this contrast is making sense. This is really all you need, to create these things. And then what happens when you do, what are these Fs? So these Fs are just activation functions, right? That we've done already as well. We talked about sigmoid, tangent. There's also ReLU, and I believe we did that one. And what do they do? Basically, the value C1, right, goes into the function, and it just gets compressed into something, right? So that's constantly what we're trying to do. ReLU does what? Drops all the negative values, lets pass all the positive values. And that works. That works, So it's, as I think I've said, some people say that LLMs, tan H, another is not a good one, right? So these are basically functions that do some processing. I was going to say, if we were doing a CNN, then we have, imagine there's going to be this input goes through a function which is like a CNN, and that gives you an output. That's gonna be it, except that it's a different type of an operation, right? That obviously we will discuss, and we'll go over the code later, and we will discuss it, later. All right, now I've done these drawings, I believe, in the lectures, right? And I just like to have a contrast, right? To give you this, this idea. All right, so here we have basically the perceptron, linear regression, logistic regression, multi-layer perceptron, and deep learning, basically. So the regression, you have all the vector of all inputs, predicts one node, goes to minus infinity to infinity. Logistic regression is a type of classification. If it's binary classification, you can get away with just having one neuron because it can be 0 or 1. Or you can have 2 neurons if you it's up to you. You will see how, as you start to get good at this, that you can do quite a bit and play with these values. Maybe the classic example in this case is to have a vector of inputs and a vector of outputs, right? In this case, cat and dog. But this is the architecture of a logistic regression model. Okay, here we have, and notice here, 0.8 and 0.4 could be the outputs. So then you just select basically the highest value. That's kind of the intuition. Multi-layer perceptron, what is it in general? One hidden layer. Okay, so you have now the input layer, right? And then you have a hidden layer, right? It's just fully connected. And then you have an output layer, basically. But remember, you can start adding these activation functions, which I've talked about already, right? Here, I'm just using an example of ReLU. And then remember, for this type of multi-class, we have softmax. So we talked about that as well. What did softmax do? In the case where we have 0.4 and 0.8 and 0.4, they do not add up to 1. However, we do know that the training data, we will know this is either a cat or a dog. So that vector will be 1, 0 or 0, 1. At those two, it's 1. So we want to give that property to the neural network, and the softmax function nicely does that for you. That's in the notes that I gave you also, and there's a Python example that you can try out if you've been reading that. And then deep learning, if you look, is just, same input layer. So you're going to have an output layer, which has a softmax, but now you just stack individual layers one after the other, okay? And you can have, 50 layers, 100 layers, right? There's problems, obviously, as you start stacking more layers that arise. So we'll see how those need to be solved later on, or how those problems were solved through something called residuals. All right. Activation functions. I have this diagram. Okay, so basically these are some of the functions that I've mentioned. There's GELU and normalized GELU and probably many more now. ReLU, which is one that does the heavy lifting. We've talked about the softmax, tanh, sigmoid, a step function, but you can see basically this is what they do. Values in the x-axis come in and they get mapped to values in the y-axis. So 0 and 1. Tanh here would be from -1 to +1, right? Softmax, we've talked about it already. And ReLU, the classic hockey stick. So all values are 0 for the positive value that come out. Any questions, guys? This is some of the terminology that we've talked about. All right. One-hot encoding, I think I've mentioned that. Okay. So we're definitely not going to cover cross-entropy or optimization today. But I guess, and we have about, 16 minutes or so. So let's just cover this last slide. And we'll kind of, stop there, and then we'll take a 10-minute break and you guys can work on your exam one. Okay. All right. As I said, hopefully you've been reading the notes, right, that I provided the link. So, there's a lot of description there. But yeah, so let's talk about this graph here. So this is an intuitive way of thinking about MSE, right? So this is just the linear regression or the regression problem, linear regression, in fact. Very simple, right? So remember, we have two equations. One equation is going to be denoted by this y hat, which I guess I don't have it here, but you should know that it is, this equation here, y equal wx plus b, okay? Right? So that you give it x and you learn w and b. And then eventually it starts to build a line, okay? Now you are doing regression, so you're trying to fit the line. You're trying to fit the line into these red dots, right? And so the intuition is, think of it this way. You have two lines, this blue line that you have here and this line that you have here. Which one of these two is better, would you say, for the data that you are seeing? Obviously, the one that fits it, right? But we also intuitively can see how the model is doing the learning. Because what you're going to do is you create, let's say, in one shot, this line. And that's your y pred. So given an x in this axis, boom, it just draws those values there. But you have the real values, which are these red little dots, right? These red little dots. So the MSE here, you can think of it as taking the difference between the predicted and the real. So for instance, here, let's take this example here, this example, right? So here, so the value is actually that one, but on the line, it is this dot. So the difference between the real and the predicted is this little thing that I drew there, curly bracket. Do you see that? So that is an actual measurable distance, right? It's an actual measurable distance on this axis here. Okay, so that's one difference. Then now take this point on x, right? So you predict that value on the function and it gives you this dot, this purple dot, but the real one was actually here for that x. So again, you take the difference. Do you see that? Now you do the same with this dot, this point here, right? So with the function that you learn, it basically tells you that it's there, but the actual real value was this one here. So you take the difference of that. If you see, we have one difference, second difference, third difference, square them, add them up, it starts to give you a value. Do you guys see that? All right. A, let's call that A. Now, let's take this exaggerated case where I have this other blue line. And how do I get, do you have a question?
I want the line actually, right? But in all these three cases, they're answering.
It's the value x, right? So x is like the input to the function, the inference function that you just learned. So whenever I have this xi, the line doesn't exist. What exists is the function. But if you ran all those x's into that function, you would plot this line. Do you see that? Does that make sense? So basically then, if you want to know at point xi, right, you would plot it, you would plug that xi into y, and it would give you this value here, this blue dot. But the real corresponding value for this xi would be this one. So now you can take the difference between the real and the predicted. Do you see that? Does that make sense? So you do that for all of them, and this, I mean, I didn't draw all of them, but this one, this one, this one, and that one, those four, sum them, and you have some value. I don't know what it is, but let's call it 36, okay? Now take the exaggerated case. What is this blue line here? This blue line here is another function, right? So another y hat. How is it different? Its w and its b is a different set of parameters, right? So that equation, whenever you plug in this xi, what happens? It plots it like out there. Do you see that? Now, if you compare, so I did it, I guess, for this one, xj here, right? So for this xj, using the other function, it plots it out here because, again, the line does not exist. What exists is this function that you created. But when you plot that function on it would look like that blue line. So I take my xj, I plot it with that new function, and boom, it puts it here. Whereas the real value is this little purple dot where I have the mouse pointing. So then when I draw this, you see it's a really big value, right? You can think of it as the distance from here to here. That's going to be something really high. And the other line, the first line that we talked about it, the first function, if you ran this xj through that function, it plots it here. Do you see that? And you compare it to the real value, which is still this same purple one. So now you see this distance. So obviously this distance is way bigger than this distance. Do you guys see that? So that's basically the intuition of MSE. All right. This is how it works. Okay. So you just take these differences and the model is just going to be doing this all the time, right? Trying weights. So it tries like a whole bunch of weights and whatever. And it's got a y, and it's always creating this blue line and getting these distances, right? These really big ones. It's like, if you add all of them, it might be like 2,000. But then you start finding another set of weights and forget how it's finding them, right? Let's just imagine you have a quantum computer, randomly it's finding them. Eventually, it starts to draw this blue line, right? And this blue line, when you compare it to the red dots, it starts to give you these curly brackets that are way smaller than these big curly brackets, because I didn't draw for all the dots, but this line would have a whole bunch of really big curly brackets. Do you see that? So whereas these values always give you like 2,000, these start to give you 55. So which set of weights do you select? You start to select the ones that gives you the lowest value, that error, basically. And that's what the idea of machine learning really is creating something that predicts, compare it to the real, and then you measure some kind of a difference, etc. Does that make sense? This is like the simplest case that you can think of, and it relates to regression, basically. Okay, and you can see here is basically taking y hat, which is the equation, as I said, key component, y hat is actually wx plus b, where w and b have to be learned. That's the thing that makes you rich, right? You create an equation, an architecture, but why, Llama 3, right? Why are people so excited about Llama 3? Everybody knows the architecture of Llama 3, but that set of weights for Llama 3, none of us can get. Only Meta, only Facebook can get those weights, right? Because they have the computing power and everything, all the data that gave them that set of weights. So we want the best set of weights for our task, basically. But in its simplest case, it comes down to something like this. Any questions? So this is just your first introduction to these ideas, kind of briefly, provide some context to some of the things that we've done in the code. And then, as I said, please read the notes. We will come back and explore these a little bit more in the future. I really don't want to get into things like cross entropy, et cetera, right now. I'm going to stay with something simple. But in summary, though, the thing that's really important that I want you to kind of, guys, the things that I kind of want you to, as takeaways, look, the contrast of the different networks, right? And the fact that we have two equations, which we did, I think, in the previous one, or two different functions, basically, which was this. This slide is actually pretty important because it shows you the inference function and it shows you the loss function, where, remember, you learn this one. This is your chat GPT right here. And this is the ChatGPT result, which gets compared to the real and gets optimized. This is a very simplistic representation of an optimization for a quadratic function. Is a very specific case. But my point is there's two graphs, okay? Just like there's two equations, and pretty much whenever we're building something with neural networks, we will be doing this. Building the architecture, which will be pretty big, that class that we built, and then building the loss function, which is usually pretty straightforward, as we just use the built-in functions in ML. All right, so I think we're going to leave it there for now. Okay, so I'm going to go back to contents. Right, so that kind of wraps up the first third of the semester. This is kind of just getting everyone situated. If you've never taken a machine learning course, you are now experts. And if you have taken a machine learning course, maybe some of this was familiar to you, right? And so that's great too. Second, third, we will start with CNNs and start, much more complex architectures. The focus, as I said, is building these models, and I'll provide some background that you should keep track of as we move forward. Okay. All right. So we have 4 minutes. So I'll remind you, there will be a homework assignment that I will be posting by Wednesday, most likely some cybersecurity data sets. You will do classification and regression. You have my code examples, but I will not provide the actual exact code for these data sets. So what will you need to do? You will need to take the code I've given you already and take that data. I'm not going to ask you to collect data. It's going to be data sets, but you're going to have to load it, build the architecture and report performance metrics. Okay. Make sense? So expect one regression and a couple of classification, and I'll ask you to do multi-layer, deep neural networks, regression, that kind of thing. Okay. Got it? All right. So that will be due tentatively 1 week from today. We'll discuss in a week. All right. Depending on people's progress with it. Yes, sir.
We turn in.
Pardon?
It's something we turn in. We don't present it.
Yeah, no presentations. I mean, it would take us weeks to present everyone. So yeah, you just submit a report, and I need to see your performance metrics and your code and things like that. You don't have to do it. Got it? Any other questions about that? All right. So yeah, it's 6:17. I'll stop the lecture here. Let's take a 10-minute break until 6:27 or 6:28, and then we will start the exam 1. Yeah, we'll go from there. Caitlin, so I see you're here, so I'll just look for the exam at 6:30, 6:28, and take it, okay? Okay, I'm not gonna Zoom, I'm not gonna start Zoom again, okay? But email me if you have any issues. I'll be checking my email. Got it? All right, great.